Happy to see in a new lesson in the framework of PLC Programming Beginner's Guide. Until now we have exclusively dealt with digital inputs and outputs. These are Boolean data type represented by a single bit that can be 0 or 1 that's true or false, in other words on or off. Digital inputs include push buttons, switches, detection sensors, etc. that are connected to the PLC inputs modules represented by contacts in PLC programming software. As to the outputs, we can cite motors, when it's just about turning on or off, and pneumatic cylinders. However, here the PLC output is not directly connected to the output device, which are commonly referred to in automation terminology as actuators. The PLC output is first connected to contactors or relays called pre-actuators, then these ones connect to the output device. Well, today we tackle the analog inputs and outputs. Contrary to the digital inputs and outputs, the analog ones are continuous signals representing various physical quantities such as temperature, pressure, flow, and level. They therefore take a range of values represented by a word data type in PLC programming. As you know, a word is 16 bits or 2 bytes in size. We can take as examples the most usual analog inputs: a temperature sensor known as thermocouple, and pressure sensor. As to the outputs, we can find control valves to control the flow of fluids, VFDs to control motor speed, to cite a few. In fact, analog devices sense a physical quantity and converts it to voltage or current signals. The most used and well-known are 0 to 10 volts, -10 to +10 volts, and 4 to 20 milliamps. The range of the device depends by large on the requirement of the industrial process. Well, unlike the digital inputs and outputs, which are represented by a contact or coil. So in PLC programming, the analog ones need primarily to be scaled, that is, making the correspondence between the physical quantity and the range of the electric signal to which it is converted. To make this, TIA Portal provides us with the scale instruction. The instruction actually carries out the correspondence between the range of the physical quantity to the target electric signal. For example, let's suppose we have a thermocouple that can sense temperature over a span of 0 to 100 degrees Celsius and converts it to a range of voltage signal 0-10 volts. In the low and high limit of the instruction we put 0 and 100 respectively. Another operation the scale carries out is converting the signal received in the input or output module to machine language. Thus, for scales are available in TIA Portal, 0 to +27,648, 0 +32,767, and their negative counterparts in case the device delivers negative signal. In this lesson we are going to simulate the thermocouple in the S7300 and S7-1500 CPU and see the difference between the two. We start with the 300. We pick from the catalog a compact CPU with integrated analog inputs. As we can see here, the CPU is supplied with 5 inputs channels and 2 output channels. Well, before we start programming and as first step of scaling, we need to set the thermocouple to its parameters. As usual, we head over Device Configuration, then on Properties. Under the analog box, we click on Input, then we select the first channel, then we enter the device parameters. As you can see here, the input supports a voltage and current signal. The thermocouple delivers a signal ranging from 0 to 10 volts. Thus we put here voltage and change the range under to 0 to 10, then we move to the inputs address. By default the inputs address starts from 800. As you know, you can easily change an input address. We keep it as it is and move to the main OB to start our program. Well, in the Conversion Operations folder we select the scale instruction. In the input we put the address of the thermocouple. The input address start from 800. Watch out to add the letter P in front of the address, otherwise the program may not run correctly. It means process variable. In the high and low limit we put 100 and 0, which are the highest and lowest values of the temperature range under which the thermocouple works. Bipolar is a parameter not to neglect. It is Boolean data type. We set to 1 when the signal range covers negative values, otherwise we set the bit to 0. The ret value shows scaling errors. In the output we retrieve the scaled output. It is a double word data type. Double word, by the way, is 32 bits in size, since it holds floating numbers. Good, we rename the parameters to see plainly and better how the instruction works. All the instruction parameters are filled. We compile the program to check eventual errors, then we move to simulation. We insert from the insert box an input variable and to memory bit, then we put the addresses of the program variables. Perfect, we can now launch the simulation. As we said earlier in the lesson, one of the scales TIA Portal uses is 0 to 27648. Normally, by setting the thermocouple to 27648, we will get 100 at the scaled value. We change the format of the scaled value to see clearly the result. In reality, the scaling puts the range of the raw physical quantity in a machine language of the CPU and retrieves the value in double word memory address to be used in the program. We test 13,824, which is half 27648, and inevitably we will get 50 at the scaled value. Indeed, we can now move to simulate scaling operation in a 1500 CPU. Without closing this current project and opening another one, all we need to do is adding a new device. Prior to that we close PLC Sim, otherwise the connection will not be established with the new CPU. Good, we click on Add New Device and get a 1500 CPU. As we will see, scaling in 15 and 1200 is a bit different from 300 and 400, however the principle remains the same. First of all, we need to add an analog input as the CPU has no integrated module. Then on Properties we set the input module to the sensor at hand parameters. As we can see here, the module only supports voltage signals and one scale -10 to +10. So, in real world this means that the thermocouple we used earlier cannot be used with this module since it's ranged from 0 to 10 volt. As a matter of fact, the features of Siemens CPUs and modules are must-know for the automation professional. The topic we'll cover in a dedicated lesson. Well, we access the main OB of the newly inserted CPU. Unlike the 300 series, scaling here requires two instructions: norm and scale. Notably, the norm instruction does not appear in the 300 conversion operations folder. Well, we drag first the norm, then we add the scale. Unlike the 300 where the physical quantity is directly scaled, here using norm, we start by normalizing the physical quantity range, that is bringing to a range between 0 and 1, then we move to scaling. In the min and max of the instruction we put -27648 and +27648 respectively, supposing that we have a thermocouple range of -100 to +100 degrees Celsius delivering a voltage signal of -10 to +10 volt. The value is for the thermocouple input, as we have just seen the input address starts from 0. Supposing that we are using the channel 0, the input therefore will have as an address IW0. The norm output is a real data type ranging from 0 to 1. It will take a double word data size. In the scale, we put the limits of the physical quantity range, thus -100 and +100 degrees Celsius. Before that we set the data type of the scale, which are in essence real numbers. The scale input is of course the normalized value. Finally, in the output we retrieve the scaled physical quantity ready to be used throughout the program. By the way, we will understand the scaling better in real-world example, which is the topic of the next video. We rename the tags and move to simulation. Perfect. The CPU is reached without trouble. However, beware, if we had not closed the 300 PLC sim, we would not be able to connect to the 1500 PLC sim. As usual, we expand the PLC sim and create the simulation project. We open SimTable and load our variables. Like the previous example, we work with some striking values as a way to grasp fully how scaling works. We start with the max value of the chosen scale. Normally, we will get 1 in the normalized value and 100 in the scaled value. Indeed. Additionally, notice below that the number 32,767 appears as the max value even if we used a 27,648 scale. This is due to the fact that plus 32,767 is the max value of TIA portal scaling range, and it is used to cover larger value ranges of analog inputs and outputs. As we see the scaling work out well. We load now plus 13,824 value, which is the max half. By reason we get 15 in the scaled value. Hope you got well the scaling concept, which is the result of a basic math operation commonly known as the rule of 3. Thank you for watching. If you find the video helpful in some way, make sure to give us a like to support us for more videos. See you in another lesson.